Our next topic is symmetric matrices. Before I do that, I want to cover one last thing that I left off of the previous discussion, which is the uniqueness of the LU decomposition and also the LDV decomposition. So the question is, suppose you have a matrix A and you write it as LU in the LU decomposition, let's say L1 U1, where of course L1 is special lower triangular, meaning 1's on the diagonal and U1 is upper triangular. And then you come back tomorrow and you do it again and you write it as L2 U2. Well, is there only one way to do this? Does that mean that L1 and L2 and U1 and U have to be the same or not? That's the question. That's the uniqueness question. Is it possible to do it with different L's and U's? And the answer is no. There is uniqueness of the LU decomposition. And the reason is actually very simple. Suppose you wrote A as L1 U1 and you also wrote it as L2 U2. Well, you could take the inverse and move the L2 over here and the inverse and move the U1 over here. And you would conclude that L2 inverse times L1 is equal to U2 times U1 inverse. You bring the U1 inverse to the other side. So I've dropped the A here, and I'm just looking at the equality of these two expressions, L1 U1 equals L2 U2, and I took L2 inverse to the left and U1 inverse to the right. And now look at this equality here. On the left-hand side, I have this thing L2 inverse L1. This is lower triangular, whereas on the right-hand side, this thing is upper triangular. So let's call this thing X, whatever it is. And I conclude that X is special lower triangular because it's equal to this thing L2 inverse L1. And on the other hand, by the fact that it's equal to U2 times U1 inverse, it's upper triangular. So somebody tell me a matrix which is both special lower triangular and upper triangular. That's extremely hard to do. So let's see. Let's write down a special lower triangular matrix. It has 1's on the diagonal, 0 above, and something below. But I'm saying it's also upper triangular. So that means I can erase this something and say that it's 0. The only possibility is the identity. So this matrix X is forced to be the identity, and that's all she wrote. That tells you that L2 inverse times L1 is the identity, which is to say L1 is L2 and U1 is equal to U2. So there's only one way to do this. So that's the uniqueness statement. And so let's state it as a theorem. Suppose A is a regular matrix. That means it has an LU decomposition. Then A is equal to LU, and L and U are unique. They're uniquely determined by A. And secondly, if A has an LDV decomposition, and all three of these are also uniquely determined. L, D, and V are unique. So this is extremely useful. There's only one way to do this, and you will see in a minute one of the reasons this is so useful. And anyway, it's saying that there's only one way to write A is equal to LU or A is equal to LDV. Okay, now I'm going to turn my attention to symmetric matrices. So before, the first step is to talk about the transpose. So if A is an M by N matrix, AT, which is a transpose, is the matrix that you get as follows. You interchange the rows and the columns. So it's an N by M matrix. And you get it by flipping A around the diagonal. So if A looks like this and is M by N, you flip it and you get a matrix of this other size, and that's the transpose. And I want to emphasize that if you start with an M by N matrix, the transpose is an N by M matrix. Okay, so let's look at a couple of examples. Well, this 2 by 3 matrix, when you transpose it, you get this 3 by 2 matrix. You just take the rows and make them columns. Alrighty, and another common thing to do is to take a vector and think of it as a 1 by 4 matrix and take its transpose and get a 4 by 1 matrix. So for example, if a square matrix, of course, stays the same size and you're just flipping it around the diagonal stays the same and the off-diagonal elements get switched like that. One way to say this, the transpose is, sometimes you write A is equal to Aij, and that's shorthand for A is the matrix A11, A12, dot, 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 up to A1n, AM1, down to AMN. This is an M by N matrix. And then A transpose is the matrix AJI. You switch the coordinates here. And what that means, really, is that the ijth entry of the transpose is exactly the jith entry of the original matrix. Okay, so that's the transpose operation. So let's look at some basic properties of this operation. So one thing that's obvious is if you have a matrix A and you take its transpose twice, you get it back again. That's clear. Also, if you add two matrices and take the transpose, that's the sum of the transposes. That's pretty easy to see. Write down a quick example. And if you multiply a matrix by a scalar, the scalar pulls out. Those are all very easy to see. But don't get complacent, because when you start multiplying matrices, something funny happens. So suppose you have an M by N matrix and an N by R matrix, and you take their product, A times B, which is an M by R matrix. And I want to take the transpose of this matrix AB. AB transpose. An obvious question is that equal to A transpose times B transpose? Looks reasonable, doesn't it? But no, the answer is it's not reasonable. It's outrageous. There's no way that this could possibly hold. And the reason is the sizes are all wrong. So A is an M by N matrix, and you can multiply it times B, which is an N by R matrix, to get this M by R matrix that I was talking about. And when you take its transpose, it's R by M. But when you try and multiply A transpose times B transpose, it's not even defined. This N by M pairs up with the R by N, and it just doesn't work if M is not equal to R. So for square matrices, at least it's defined, but the fact that it doesn't work at all for non-square matrices is what's telling you that it's just not right. But now notice, there are these two N's here, and if you switch the order, then it looks reasonable, right? Because if you switch the order, if you took B transpose A transpose, that would be R times N by M would be R by M, and that kind of looks right. And that's absolutely correct. The transpose identity is correct, except you switch the order. B transpose is B transpose A transpose. And again, I like this little argument here involving the size of matrices, because it makes it clear that even if you're using square matrices, it's not reasonable to ask that this be true without changing the order. So let's do an example. Let's take a matrix, a 1 by N matrix, and I'll call it V, and take another 1 by N matrix and call it W. And I can take V, well, let's see, let's write down W transpose. That's a column vector B1 through Bn. And I'm being careful now about column and row vectors. You can take the product of the matrix V and the matrix W. Excuse me. I don't want to write dot there. It's not the dot product. It's the actual product of matrices, and it looks like this. And it's a one. The result is a 1 by 1 matrix, which is to say A1 B1 plus dot 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 AN BN. So that is the dot product of V and W, the usual dot product. So the product of these two matrices, this row matrix or this row vector times this column vector, is the dot product. And if you do things in the other order, if you take W times V transpose, if you take this thing and take its transpose, that gives you W times V, W transpose times V transpose. And we already saw these two transposes cancel. And you get W times V transpose. And if you write that out, that's B1 through Bn times A1 through An. And you get the same thing. It's the A1, B1 plus dot dot dot, so on. And that's the dot product in the other order, W dot V. And of course, V dot W is equal to W dot V. And this all makes good sense. Okay, so that's an example and a kind of operation that comes up quite often. Now, another very useful fact is that the transpose and the inverse commute. So if you take the transpose of a matrix and then its inverse, it's the same thing as taking its inverse and then the transpose. It doesn't matter what order you do these operations. So let's just write down an example. Let's take A to be the matrix 1, 2, 0, 1. A transpose is this matrix. And A transpose inverse is, by the formula for 2 by 2 matrices, this. On the other hand, if I do things in the other order, A inverse is this matrix, 1 minus 2, 0, 1. And then the transpose of this is 1, 0, minus 2, 1. These two are equal. So transpose and inverse commute, meaning it doesn't matter which order you do them in. And it's useful to note that this operation of doing both of them, A transpose inverse times B transpose inverse, is equal to A times B transpose inverse. Because when you do one of them, it switches the order, and then you do the other one, it switches it again. So even though transpose, you have to switch the order, and inverse, you have to switch the order, when you do them both, the formula comes out with A and B in the same order. Okay, now we can talk about symmetric matrices. Take an n by n matrix A. It's said to be symmetric if A transpose is equal to A. Okay, simple enough. And here's a couple of examples. Any 1 by 1 matrix is symmetric. A 2 by 2 matrix is symmetric of this form. The off-diagonal elements have to be equal. So for example, 1, 2, 2, 3. Another example is if you take a matrix like this, as long as you put the same numbers below the diagonal as above them, then it will be symmetric. And here's a symmetric permutation matrix, just as an example. So all of these matrices are symmetric. If you take the transpose, you don't change them. Okay. So now I want to talk about the LDV decomposition of a symmetric matrix. So this is symmetric matrices have a special LDV decomposition. So let's just start off with a quick example. Suppose A is 1, 3, 3, 2. What's the LDV decomposition? Well, the LU and then the LDV decomposition of this matrix. So let's see. So you take 1, 3, 3, 2, and you have to multiply the first row by minus 3 and add it to the second, and that will turn it into 1, 3, 0 minus 7. And so let's see, so that's upper triangular. So that's my LU decomposition already. I have that this matrix is equal to this product, 1, 3, 0, minus 7. And for the lower triangular matrix, I take the inverse of the thing that had a minus 3, which is to say a plus 3 here. So that's my LU decomposition. And then I refine that to get the LDV decomposition. I keep the diagonal entries, 1 minus 7. Right, so here I'm writing U is equal to dV, and I keep the 1 minus 7 and make a diagonal matrix like that. And then I make an upper triangular matrix. And let's see, I need to put 1s on the diagonal, and in order to make this come out to be correct, I have to put a 3 here, so that D times V is equal to U. So that's the LDV decomposition of this matrix. 1, 3, 3, 2 is equal to this. And LDV. And you, right away, you notice, well, that's nice. These two matrices, L and V, are each other's transpose. And that's interesting. If you take a special lower triangular matrix and you take its transpose, you do get an special upper triangular matrix. And you can ask yourself, is this a general fact about symmetric matrices? And indeed it is. So suppose you have an n by n symmetric matrix. So the statement is that A has an LDV decomposition, which is to say it's regular, if and only if it has an LDL transpose decomposition. So a symmetric matrix, if you can write it as LDV, then you've written it as LDL transpose. The only way to do that is LDL transpose. So here, of course, L is special lower triangular, D is diagonal with, as usual, non-zero entries on the diagonal. So the significant thing here, again, is that this matrix on the right is not V, but L transpose. And the reason this is true is very elementary. It's nice to explain why. Suppose you have a regular matrix, so it has an LDV decomposition, LU and then LDV. So find one, write it LDV, whatever. Now take the transpose of A. So A transpose is, well, A is LDV. So write it as LDV. And take the transpose of that, and you get V transpose D transpose L transpose. And D is diagonal, so this transpose goes away. D transpose is equal to D. And you've written A transpose as V transpose D L transpose. Well, let's see. I said A is symmetric, so A is equal to A transpose. So A has two decompositions, LDV or V transpose D L transpose. Both of these are LDV decompositions because the first matrix is lower triangular and the last matrix is special upper triangular. So by uniqueness, you conclude that L has to equal V transpose and V has to equal L transpose. So for a symmetric matrix, the L and the V are necessarily each other's transpose. That's the main point here. It's also worth noting that sort of going in the other direction, if you have a matrix of the form LD, L transpose, if you take its transpose, you get this, and most of these T's cancel. Those two do, and that one because D is diagonal, and you get LD, L transpose back again. So a matrix of this form, LD, L transpose, is automatically symmetric. And so that's what this theorem is about. So for symmetric matrices, the decomposition is the LD L transpose decomposition. Now, one nice thing here is that when you have a symmetric matrix, if you're trying to find its LDV decomposition, you only have to do half as much work because once you found L, you know that V is L transpose. So you can use that and stop your calculation sort of halfway through. So let's do an example of that. Suppose A is the following 3 by 3 symmetric matrix. And let's suppose that we run the Gaussian algorithm on this to find the LU decomposition. What am I going to do? I'm going to add -2 times the first row to the second. And I'm going to add -1 times the first row to the third. And that's going to convert this matrix into, what do you get? You get 1, 2, 1, 0, 1, 1, and then the last row becomes 0, 1, 3. Okay, and then one more step is you add -1 times the second row to the third. That should be -1, not a -2. And that will convert this to 1, 2, 1, 0, 1, 1, 0, 0, 2. And that's upper triangular. So that gives you the LU decomposition of this matrix. So let's recover that. L is, remember, we have to go back and multiply these three matrices together with the inverses and such in the right order. What you do is, it's these three matrices, you first put the one to the right, you put a 2 there, and then the next one you put a 1 there, and then the next one you change this -2 to a -1 because you realize that's what it should have been. And in the bottom entry of this third matrix, you put that 1. And this is my L. And if you just multiply those out, it turns out to be this thing, 2, 3, 1. So that's L. And now I'm done. I found L. And because this matrix is symmetric, I'm basically done. So there's L, and I had converted A to this thing here. And you just pull out the diagonal entries, and that's D. And then V is L transpose. So the answer is A is equal to L, D, L transpose. And notice that I didn't have to do any further work in order to find this third matrix. Okay.